Hi everyone, we are from Group 5. Let me start the presentation. This is our research title, Automated Repair for PHP Program Bugs Using Deep Learning. This is Automated Program Repair workflow. First, developer would provide bug report which indicate bug, and these are steps to reproduce along with the test suite. So program repair can automatically find what locations to fix and generate patches and validate using provided test suite. Then give list of plausible patches. We call them as plausible patches, and programmers can decide most suitable patch. We call them correct patches. Instead of developer going through debugging, generate patches and validating, automated program repair can do this step for developer and generate list of patches. Developers only have to review this list of patches that have been generated. We develop a deep learning based automated program repair tool to create more correct patches for bugs in PHP programs. We curate a PHP bugs training and testing dataset, then analyze the performance of the large language models and state-of-the-art automated program repair tools on newly created PHP bug dataset. Then develop a deep learning based automated program repair tool that utilize fixed ingredients to generate more correct patches for PHP bugs. This is the creation steps of bugs PHP dataset. This dataset consists of two parts, which are training dataset and test dataset. Training dataset contains only buggy version file and fixed version file. Test dataset contains the whole buggy version of the program and fixed version of the program and the test cases. Let's move into bugs PHP test dataset creation process. First step is subject selection. We use the GitHub REST API to retrieve GitHub repository list. We set language PHP and latest commit date should be date after 2020, 1st of January of 2021, and sort by status count in the descending order as shown here. Then we remove the repositories which do not have test cases by manually, and then select the first 75 repositories. The next step is bug collection. First we clone all the repositories that we selected in the previous step. Then we collect all the bug fix commit with these terms in the commit message: fix, solve, bug, issue, problem, error. Then we apply following criteria to filter out unusable data. Next step is manual validation. After the bug collection, we manually check that the test cases were being run in each repository by running test cases for latest bug fix commit that we collected. For this, we choose PHP version 8.1 because currently it is the latest stable PHP version. After this step, we removed some repositories that could not run test cases due to some issues like PHP version incompatibility. Next step is dynamic validation. In automated program repair, there should be a way to identify whether the generated patch is correct. To do that, at least one test case should be passed in the fixed program version but failed on the buggy program version. We examine each bug to guarantee that the above collected bugs match with this requirement. After dynamic validation, we get the bugs PHP dataset. This is the number of bugs included in our test dataset from each project. Overall, we have 513 bugs included in the test dataset from 15 repositories.
Let's look at our training dataset creating process. We use GitHub REST API to retrieve the repositories according to the same criteria used in the above test dataset subject selection. Then select the top 5000 repositories. Then we remove the repositories that we used to create test dataset and collected more than 500,000 bugs from those PHP applications. In the cleaning and labeling steps, we remove all other files and only keeping PHP files with changes. Then we label those files into buggy and fixed version. And finally, we include a metadata file including the meta information such as repository name, bug ID, buggy and fixed version commit IDs, and buggy line numbers, etc. Let's look at our empirical study. We use two large language models which are TextDaVinci 003 and GPT 3.5 Turbo, the model behind the ChatGPT. Also, two state-of-the-art repair tools, Kio and Reward Repair. And let's look at empirical study of large language models. This is the high-level diagram of patch generation with large language models. First, extract the buggy line and its context. We use two query type as prompt for the model. For both query types, we get context as maximum 40 lines above and below the buggy location with including buggy line. But in query type 1, we didn't specify what are the buggy lines as in query type 2. In query type 2, we provide buggy lines as additional information to the model. Third, we call the API provided by OpenAI to generate patches from model. Then we preprocess every patch to remove some unnecessary word. Next, replacing those generated patches in original file in the project and run the related test cases to identify plausible patches. Finally, we manually compare against the developer fix to determine semantically equivalent patches and identical patches. Next, I will present about our empirical study using state-of-the-art repair models. This is the high-level overview of the training process. This is the high-level overview of the inference process.
In this section, we aim to propose a learning-based APR tool, PHP Fixer, the first multi-encoder APR approach to repair PHP program bugs. This is our APR tool workflow diagram. First, we extract the buggy line and buggy context. Also, it extracts the additional fixed ingredient for the buggy location, such as local variable within the buggy function, global variable and the function name within the buggy file, and type information. Then combine the buggy line and buggy context as a single input text sequence, and additional fixed ingredient as another single input text sequence, and input to the PHP fixer model after the tokenization. Then we generate 100 candidate patches for the each bug in the test dataset and did the same validation as in generally. Encoder-decoder transformer model has one encoder and one decoder. It can translate one source code into one target output. Existing work on machine translation shows that using a multi-encoder approach is beneficial when utilizing additional information for the machine translation. Therefore, we adopt that approach. While they propose multiple ways to combine two encoder, we use serial approach because serial approach strategy perform better in multi-source machine translation tasks. This diagram shows that the two encoder model architecture combined according to the serial step used in our model. According to our experiment result with existing APR tool, pivot repair tool performed better with PHP bug data. Pivot repair was used T5 model, so we select T5 model as our base model. We added one additional cross attention to the decoder and connect the second encoder to it. For the first encoder, we provide additional fixed ingredient. To the second encoder, we provide buggy lines and buggy context as input. Let's we look at result comparison. Here, first chart shows result of the path that passed the failing test case. In that case, our tool has the highest result with 57 patches. In the second chart shows result of the pattern that passed all the test cases. In this case, TextDaVinci has most possible patches, which is 30, but if we consider the existing APR tools only, our PHP fixer has the highest result of 19 patches. And here shows result of the semantical equivalent patches and developer identical patches. By comparing semantical equivalent and identical patches of all the models, we can see both large language model has the most number of semantical equivalent and identical patches. But among the APR model, PHP Fixer generates more semantical patches. We integrate our PHP Fixer tool as Visual Studio Code extension. This is the high-level architecture of the extension workflow. PHP Fixer extension is installed into the VS Code editor and model is running separately as a server. When user requests bug fixing, PHP Fixer extension sends the post request to the server and generate the requested number of candidate patches and send back to the extension. An extension replaces those patches with the buggy line one by one and execute the test cases and list show the possible patches. First, we look at our demonstration. First, we need to start the server, and I already started it, and server export port number 8000. And also, I already installed the PHP Fixer extension to my VS Code editor. Let's consider this PHP program. This program doesn't have a bug. I can show it by running the test cases. Test cases are passing, so there is no bug in this code. Then I'm going to make a bug in this code by changing this line. I change this number as a 2, and now there is a bug in this code. I can show it by running the test cases again. Test cases are getting failed. So there is a bug in this code now. Now I am going to fix that bug using PHP Fixer. To do it, I select the buggy line and right click on it there is an option here, fix PHP bug, and click it. And we can see here the status now is generating the patches, candidate patches. And now it's running the test cases on candidate patches. Here it is, we have generated 5 candidate patches and it's running the test cases one by one. And after executing all the test cases on each candidate patches, if it found any possible patches, we can show those possible patches as here. And then developer can keep the patches he wants and remove the other candidate patches. And this is the one possible patch for this bug. And I can show it by running the test cases again. Test cases are getting passed, or PHP can fix that bug. Demonstration is over. Thank you.